please. Yeah. And the last speaker this morning session is Lorenzo Zambotti from Paris 6, and he will speak about hot scatterers, etc., etc. Please welcome.
Thank you very much. I'd like to thank the organizers for the invitation. Now, I want to report on a recent research that is in collaboration mainly with Raphaël Lefebvre, a colleague in Paris. And it's a model for the transfer of heat, so a model based on collisional dynamics. And so there are mainly three parts. So the first is the model, the introduction, main results, and discussion of the relevance for statistical physics. This has already been written down with Raphael. Then a second part, which deals with the large deviations of the model. This is in collaboration with Raphael and with Mauro Mariani, and it's in the course of being written. And then a last short part about scaling limits, fluctuations, and associated SPDE, which is essentially still in project. Now, heat conduction is a classical problem which dates back to Fourier. It's still very large, so still largely open and very actual. Actually, many of us noticed this in their rooms in the college, so where it's heating conduction has some problems. Now, so the main problem I want to discuss is in one dimension, where you have let me draw a picture. So you have a medium, and on the left you have a heat bath at temperature TL. On the right, a heat bath at temperature TR. If the temperatures are different, then we observe in real models a flow of heat. For instance, if TL is greater than TR, then there will be a flow of heat in this direction, and a temperature profile will be observed, right? So at some position here, there will be a temperature Tx, and okay, so you can study a stationary solution, or you can study a non-stationary solution. So there are many variants of this problem. Now, for instance, we can ask in a steady state what the temperature profile you observe, which will be constant in time, but not in x. And this is a very typical non-reversible process. And in statistical mechanics, it's called a non-equilibrium situation. So it took me some time to understand the relation between the say probabilistic and the physical terminology. And so in this case, I think this is correct. And now, in principle, the most realistic mathematical model should involve some random description of the heat bath and of their interaction with the medium, and then some purely deterministic dynamics in the medium, in the bulk, right? And for such a system, there is a huge physical literature, and also a huge mathematical literature. So physicists still do research, but so their comprehension is relatively so advanced. While for mathematics, many problems are still open. So there is a huge literature. So I will not mention essentially anyone. So in this way, I don't risk offending the others. Okay, but really, okay. Now, the Hamiltonian model is the most popular, essentially, and this is the perhaps the most classical one in one dimension. So you consider a Hamiltonian model perturbed by stochastic. So okay, let's see how it works. So this is like a solid, and it's like on a microscopic. So a microscopic description is a number of particles on a lattice, and the particles are more or less not fixed, but almost they have a little bit of freedom, but not too much, because they are in a solid, they're in a lattice, and so they are okay, they are like constrained. Okay, and when one moves, it will communicate some force to the neighboring one, and this will this interaction will move through the system, and so you have an energy which is written like this. So this is a potential energy plus a confinement energy plus an interaction energy. Okay, and now the Hamiltonian system associated is so purely Hamiltonian in the bulk, and it's Hamiltonian plus Orsten-Uhlenbeck say correction on the left and on the right. And you see the temperature of the heat bath appearing here. So you have a T0, which is equal to T to the left, Tn, which is equal to T to the right. And so this is an example of what I was telling you before. Stochastic model on the boundary and deterministic model in the interior. Now, when the two temperatures are equal, this is the equilibrium case. Actually, in this case, many things are known. For instance, the invariant measure, so which is unique under certain assumptions. Now, of course, I'm not precise, but essentially the invariant measure is explicitly known. It's just a Gibbs measure, exponential of minus 1 over t, the Hamiltonian. Although the system is not gradient, right? This is a different setting. It's not a gradient system, but still you realize that the invariant measure is this one, while for different temperatures the invariant measure is not explicit, and this is the non-equilibrium case, which is the most interesting one. Now, this is the classical model, but it's not the one I'm going to consider. So I'm not going to consider Hamiltonian model. I will consider collisional dynamics as in the title. And so what is this? So before going to that, I show you a picture of. Let's see if this works. No, it's not. So sorry. I have a picture to show you, which is, this one. So what is this? This I have downloaded from internet. It's an aerogel. So let me write this. So this is a strange material. That you can see. So I was told that you can see an aerogel in the Aerospace Museum in Washington, D.C. So Sandra, you can next time you go, because this is used in applications for I don't know, for satellites, or don't know very well what. So it's a strange material which is halfway between a solid and a gas. You see, it's a solid, but you can see through it a little bit. So it has an atomic structure of this kind. There is a three-dimensional lattice, which is here just two-dimensional, which makes the solid part of the material. And then inside there are atoms which are trapped in these boxes. And atoms can move freely inside the box, but they cannot get out. And how do they interact? Well, there are some holes, let's see, at atomic level, of course, it's difficult to figure out very well, but they can interact when they hit each other through these holes in some sense. Okay, so this is a mixture of a gas where particles can so interact by collision, and a solid since they are more or less trapped inside a lattice.
Can they move through those holes?
No, they cannot. They can just exchange energy by collision, but each is trapped in its box. So in some sense, you can imagine here you put a heat bath on the left. Okay, so here you put TL, here you put ER, and so you will heat these particles, and they will interact with the neighbors, and so on and so on. And so the temperature also will, so the heat will also flow through the system.
Can
Now,
I ask a question?
Yeah.
How do we think about the scaling of the number of particles per box? Is it order 1, small, or large?
No, okay. In this description, there is one particle per box.
Is that the way it is, or?
Okay, so you should go to the Aerospace Museum.
Actually, I went in July, but I didn't see it.
So I've never been in the outer space, so I don't know the details. So I know, for instance, my co-author Raphaël Lefebvre could tell you more about this, but so for instance, okay, so he wrote a paper in the physics in a physics journal about this kind of model where you have deterministic dynamics in the bulk, and again some form of random interaction with the boundary. Now, okay, so where is the other file now? Okay. Now, another model has been proposed by, okay, actually there are many models. So Ekman and Young, which is so related but kind of different. So they propose, again, a one-dimensional system where you have, say larger, they say some kind of tanks of energy. So these are kind of black boxes. There is a particle here which starts, moves freely. So here it's a uniform motion. When it enters the tank, many things happen inside. And when it gets out, essentially the speed is new and independent of the previous speed. Okay, so they have a very long description of what can happen inside, some kind of, say, chaotic billiard. So the particle will do a lot of complicated bouncing back and forward, and so they try to justify the assumption of independence and so on. And now, when it goes out, it will move to the next. Here it will be again uniform motion, then it will go to the next tank, and so on. Okay, so they propose two systems. So one where the particle will do this, so move from the left to the right, and then back again, then back again, and there will be many particles which do this. And this is the first. Did they give a name? So not so yes. So moving freely. And another one where actually each particle is trapped between two tanks. Okay, the second system looks like the aerogel, so as I say, with a lot of work, they propose two different temperature profiles. So again, the problem is this one, to understand if I put the temperature here and the temperature here, what is the temperature in between. Now they have a linear temperature for the wandering case, so where the particles move freely, and a nonlinear temperature when the particles are trapped. Okay. Now, okay, we have more or less try to find a mathematically tractable model which looks like this one and this one, so which tries to capture the relevant properties and which is so simple enough to be treated. Yeah. So now I'll move to our model. So once again, I didn't say this, I forgot. So in this case, in the Hamiltonian case, the invariant measure is Gaussian in P. Moreover, you see it's independent. P and Q are independent. It's a product measure, right? And it's Gaussian in P, which is a very nice property related to the Maxwell-Boltzmann distribution and so on. So this is a property which is somewhat nice, so we would like to keep this. And so again, in the equilibrium case, we would like a Gaussian probability measure in P. Okay? And in the non-equilibrium, it should be a kind of perturbation of this, at least if we are close to equilibrium. Now, the SDE approach is not the only way to have such an invariant measure. So another one is the following. So I will describe now inside one box of this kind of system what happens. So now this is just the building block, and then you can use this to build the other models. So you have here one tank of energy at a certain temperature T, and this emits a particle, okay, which has a random speed, and the speed v is distributed according to a probability distribution phi, and then starting from 0, so say this is 0, this is 1, the particle moves of uniform motion from 0 towards 1. Okay. When the particle arrives here, it is absorbed, and okay, in the building block, it is re-emitted from this wall with another speed, which is independent of the previous one, but with the same distribution. And then this goes on. Okay. Yeah, so this is the idea. I hope I explained it well. Now, this is a formal description of the system. So you can have actually an initial position. So suppose at time 0 you are here. This is Q0, and you have speed P0, which in this case is always positive. Now, it will take a time S0, which is 1 minus Q0 over P0 to reach 1. And then you will be, so the particle will be absorbed, re-emitted with a random speed. And then this process I was telling you before will start. So you see, you move of uniform motion up to the first hitting. And then, so actually the description is very simple, but I need some, okay, I will erase the aerogel. So this is time, this is 0, this is S0, which is deterministic, and then you start, you have the first time, the second time, the third time, the fourth time. Now, of course, it takes a time 1 over V1, okay, to cross the box, then a time 1 over V2, and so on. Okay, so I will call these times tau, and so on. Now, what's the description of the process? You pick a time, a deterministic time t, which will be, say, here. Okay, so here it is tau 3. Now, here your speed is v3. So here your speed is v3. And your position is what? So you take this time interval, which is along tau 3. You multiply or divide by whatever is needed to carry it to 0, 1. And then you check where your position is, right? So it's really a simple process. So you could even think it's insulting for SPDE audience to talk about such a model, but you will see there are several surprising things which arise. Now, for instance, you could wonder, okay, this is a Markov process. It's easy to see. It has a unique invariant probability distribution, which is uniform in space, and it's almost Gaussian. So it's the positive side of a Gaussian. Now, this can be kind of surprising because you are updating your speed at a so with a probability distribution which is phi, which is not this one. It's this one times p and then a constant. Okay. So why is this surprising? Because if you sample, you take t, deterministic t, the speed of pt is v3. So it's some element of the sequence. Okay. So all elements of the sequence are IAD with the same distribution, which is phi. So you could say, well, pt also should have this distribution phi. Right? Where is the mistake? So the mistake is actually very classical. It's the classical paradox of the bus stop. And it's the fact that you are taking an element of your sequence, but it's a random element, and the choice is not independent of the sequence. It's it depends very much on the sequence. So you are choosing a particular element, not any element, but a particular one. So it's not the same as a fixed as V1. In particular, you can see that it's easier to select a large element tau rather than a small element tau. Okay, so here I was not lucky. I picked the smallest one, but actually it's easier to be here than to be here. Okay, so actually you are choosing an element of your sequence, but with a bias which favors a large tau, which means which favors small v. Okay, and this is reflected in this fact. Okay, so there is a difference between the update distribution and the invariant measure. So the invariant measure is what you want, but so in order to have this invariant measure, you must have this probability distribution. Now, let's go on. Now, of course, this is a building block that you can use to describe any model of this kind. Okay, so each box behaves like that. So you're going to choose actually arbitrarily temperature here, which are fixed. Okay, so this is an important point. For the moment, temperatures are fixed and arbitrary. Okay, I will fix the temperatures later with some consideration. Notice that I am not giving a very realistic model in the sense I said at the beginning, because I'm putting a random say effect also inside the bulk of the system. So not only at the boundary. Actually, in this situation, each tank of energy works like the heat bath. So this is not physically very optimal. On the other hand, I will show you some properties which capture what happens for deterministic systems for which simulations are done easily. And so the interest of the model is perhaps twofold. So first, it captures some real properties, and it's tractable enough to make a lot of computation. Now, again, like in the case of Ekman-Young, we consider two extreme cases. So one in which the particle will cross the whole system before coming back. It's called the wandering traces, and it's the first model proposed also by Ekman-Young, the one which gave linear temperature profile, and the second one where each particle is trapped inside each box. We can also consider cases where you have a probability, non-trivial probability to go to the left or to the right and so on, but so this is covered, but for simplicity I prefer to stick to this case. And then okay, these are the expressions of the invariant measures. So this is for the wandering traces, so when you go through the system, so you see it's still kind of a combination of half Gaussian distributions, product with some space variable, and okay, so this is it. Now, okay, for physicists, a crucial quantity is the current, which means the flow of heat from, for instance, left to right, and which can be described as the energy exchanged from 0 to t between, for instance, this tank and this tank. Okay, so once again, a tank gives a kinetic energy to a particle, which moves, goes to the other tank, and gives its kinetic energy to this tank. And then the thing can start again. If it's trapped, this tank will give another kinetic energy to this particle, which will go back. And so there will be an exchange between the two, say, walls or tanks of energy. Now, physicists are very much interested in computing this, because again, it's a measure of how the heat flows from one side to the other. And so in general, for instance, for Hamiltonian models, these computations are quite difficult. In our case, it's quite easy. And we find this expression, so the current of energy per unit time is this. Okay, so it's a constant times the difference of the temperatures, and the constant is explicit, so it can be computed in this way. So in the case of the wandering traces, it depends on all the temperatures of the system, while in the case of the trapped particle, it depends only on the two temperatures, so which are relevant, which is kind of obvious because in this case the particles are independent of each other. And so this Kn is essentially a frequency of collisions between the tracers and the walls. And this, okay, again, seems to be, so it's correct, it's the same in deterministic models for which one can only do simulations and not precise computations, and is what is expected, for instance, in the aerogel model, where the exchange of energy happens only at collision times, and so the frequency of collisions, of course, must enter into the picture. Okay, but these are really very simple computations, essentially based on the renewal theorem and things like that. Now, so as I said, up to now, temperatures are completely arbitrary. So this is not, of course, very reasonable. So we should impose some condition, namely that energy is almost preserved. Okay. So now, for a Hamiltonian model, energy in the interior is exactly conserved. Now, in this model, it is not, but we can ask at least for conservation of energy in the steady state, right? So in equilibrium, in a steady state, we want that the we want what? So this condition that Jn is equal to Jn minus 1, where Jn is this current of energy per unit time. Okay, so in some sense, the energy which is transmitted from this to this is equal to the one which is transmitted from this to this, and so on. So there is a constant flux of energy, and this gives an equation on these quantities. Now, at this point, everything just depends on this set of temperatures, and okay, in the limit when n goes to infinity, we can prove so rigorously and easily that indeed these two profiles are recovered. So the temperature, the linear profile, which is somewhat typical of many models, and the nonlinear profile, which is more interesting and is so more difficult to find so to derive rigorously in Hamiltonian models and things like that. So this seems to be, again, I am not particularly expert of statistical physics, but this seems to be really an interesting profile to obtain in a model. Okay. So I hope now. Again, many explicit computations can be done. One can check that a number of classical formulae which are expected for this kind of systems are correct. So I could spend some time on this, but I don't want to. So this is just to say that this model seems indeed to be reasonable, because many things are correct as they should be. So there is one more computation that we can do. So again, we consider Jn is the current of energy, so the amount of energy that has been exchanged between two tanks, two neighboring tanks, up to time t. So you multiply by lambda, you take this function and this limit. Okay, so this is a cumulant generating function, and this is related to the Legendre transform. So this is the Legendre transform of the large deviations rate functional of the current. Okay, so this is interesting for, again, it's a quantity that physicists always try to estimate or to compute. So mainly this or the generating function, if that's only that's all they can do. And now, okay, this is a point which deviates from the standard theory of physics. It turns out that Fn is not analytic. So this generating function, Fn of lambda, as a function of lambda, has this behavior. It's something like this. Okay, so Fn of lambda. While in most, essentially, I think all cases which were known up to now, it would have been something like that. Okay, so we don't have this this part. It's just flat here, and then okay. So this is surprising, and so there are two possibilities. Either this is an artifact of the model, which is not correct for this, or in collisional dynamics, this is natural, and it's not observed in other models because aerogels are different from wood. You know, right? So, so again, I don't really know for the physics. We don't really know what the answer is to this. We shall try to do some simulations to check if one can see this. But for the moment, we started to try to look at this problem mathematically, and it was it produced a lot of fun. And so we will try to explain this mathematically. Okay, so physically, I don't know, but mathematically, it's quite nice. So the reason why you have this flat part is essentially, you see it in the proof, the presence in your system of slow particles with relatively big probability. So you have a polynomially. So I say, yeah, I mean, I said polynomially small, which means rather big, okay, compared to exponentially small. Okay, so polynomially small probability to have a small, a low speed. Okay, so this is the simple computation. Okay, and so this is, you see it very well in this graph. And now perhaps it's interesting to try to understand this in a more so complete way. How? Okay, so this is, sorry, the beginning of the second part in collaboration with also with Mauro Mariani and Raphaël Lefebvre. So perhaps the most complete way, or one of the most complete way to see this is to try to compute the Donsker-Varadhan large deviation principle for this Markov process. Okay, so again, I come back to the building block. I could explain you the big system, but then we would be late for lunch. So I just stick to the easiest, so the first model, the building block. I remind you the definition. Okay, you still have here on the blackboard, and I just add this definition. Nt is the total number of collisions up to time t. Okay. Now the Donsker-Varadhan large deviation principle concerns the empirical measure of the Markov process up to time t. Okay, so it's this. You take a Dirac mass along the trajectory and you integrate in t, and you normalize, and you get this. Okay, so this is kind of complicated, but you can write this explicitly as a function of the sequence of the speeds, vi. Okay, so you see you have vi, you have nt, you have s, which is the sum of the. So s is the sequence of the subsequent collision times. Okay, Sn is the sequence of the collision times, Nt is the number of collisions up to time t, Vi is the sequence of the speeds. So you can write almost explicitly the thing like this. So perhaps this is a simpler version. So alpha t is this, Snt over t. dq is the uniform measure on 0, 1. This is just a function of p. And then you have this part which corresponds to, you see, when you are here. So you have not completed yet the last crossing of the interval. Okay. So in Q you have only a part of the interval 0, 1, which is okay. You have not. So you have a last term which is not the Lebesgue measure on the whole interval, but just on a sub-interval, which is what you have crossed up to now. Now, it can be seen, rather easily that this converges to gamma. So what does it mean? It means that this part goes to 0, so actually alpha t goes to 1, dq is already there. This converges to the Gaussian, and this goes to 0. Okay, so this is correct. Like ergodicity, your measure, so your empirical measure goes to the invariant measure. Okay, so this is essentially ergodicity. But we want to study the large deviations. So what will be a possible value of mu t, which is not gamma, which happens with low probability, but still can happen with some probability as t goes to infinity. So actually, this will be read off from this formula, and I try to explain this next. Yeah, okay, so of course the large deviation principle is something like that. So you take some set of probability measures. You want to study the probability that mu t is in A, and compute some asymptotic of this kind with a certain functional I, which will be which we will have to identify. Now again, I write again this expression. So notice that in this case, tau, which is 1 over v, has polynomial tail. Okay, because tau e greater than t corresponds to v. So tau I greater than t corresponds to vi less than 1 over t, which has this. So the inter-arrival times are big. Okay, they have no exponential moments, and in particular, the classical theory of large deviations does not apply so applies neither to the sequence of collision times nor to the counting process of the collisions. Okay, so you can write this as a function of Sn and or Nt, but you cannot deduce the large deviations of this from the large deviations of the two standard objects, because you are in a situation where you have no exponential moments. So Sn over n does not satisfy a standard large deviation principle. And okay, yeah. Now, when t goes to infinity, you see this structure will be preserved. So the only measures mu for which the large deviation rate functional can be finite are those who respect more or less this structure. So you can have alpha p dq. You could have that this pt converges to the Dirac at 0, and then you will have possibly a term like this, or you will have something which is the limit of that. Again, a Dirac at 0 in p, but then dq on an interval, okay. So if you want, it's a kind of a topological argument that mu t belongs to a certain convex set, and then closed set, and then in the limit only this closed set can have a finite large deviation rate. So there is a description. Perhaps I will not spend too much time on this, and then we can write explicitly the large deviation functional as follows. So I of mu is mu of p, which is mu of p, also like here. So mu of p is the integral of p in d mu, so it's the mean of mu, times the relative entropy of a certain transformation of pi with respect to phi. So I'm sorry. Pi is this component. Okay, so it turns out that the large deviation functional depends only on this first part of the measure, and this is the expression. So it's explicit. It depends on the mean, which is related to the collision frequency. So it should be there, and then you have this relative entropy of the transformed equation. So this is quite nice for many reasons, but so we will not have time to explain them all. But here there is a particular feature that you see. If you don't have this part, then you integrate p here and you obtain 0. You see, because here's a Dirac delta at 0, Dirac delta at 0. So in particular, if you don't have the first part of the measure, then this is identically 0. Which means that, in fact, this large deviation functional vanishes identically on a set of dimension 3, which is the parameters, which is so not what you expect for a typical large deviation functional, which should vanish only at the limit of the equations of the sequence. Okay. So now, by contraction, one can recover the large deviation functionals of many observables, like the current, the energy, and many other. I say here almost explicitly. Why? Because typically a contraction argument gives you a rate functional, which is a minimization of this one. Okay, so the minimization is over a very big space, and so it's typically not very explicit. Actually, in this case, you can reduce to a minimization over a one-dimensional parameter. So it's really almost explicit, and this is due to the fact that here you have an entropy, and minimization of entropy is a rather so well-known topic. Okay, so once again, the explicit expression helps somewhat. Now, a rather so nice feature of this model is that Donsker-Varadan have a general formula for this kind of rate functional, which is the following. So you consider the generator of the Markov process, and you take this supremum over positive g, and this is an expression for the rate functional. Okay, so the generator of the Markov process is very, very bizarre. So this is the part okay, which you expect, the Hamiltonian part, say, but there are boundary conditions which are very strange. So the boundary condition is that the value yeah, you see you have p and q, so the value when p is 1, when you are on the right, when you are here, is equal to an integral of the value when you are on the left, and the integral is with respect to v, and the updating distribution comes in this way. So so it turns out that if you use this formula with this definition, it's not the right expression, because, well, you see, again, delta 0 will integrate to 0 this p, and so you will get 0 for too many measures. Okay, so we know that nu in the q must be of this form, otherwise this would be plus infinity, while for the classical Donsker-Vara formula this is not what happens. Now so just a slide. So the process is not failure. So this is one of the hypotheses of the Donsker-Varadan theory for diffusions, for instance. Moreover, the generator is kind of strange. So if G is differentiable, okay, so but does not satisfy the boundary condition, so G is not in the domain of the operator, then still the semigroup is differentiable at 0, but it's not continuous in T. So somewhere it will there will be a jump in the function Pt G QP. So it does not belong to any class that I am aware of. So you see, it's discontinuous, but not in the way a Lévy process would be, because the jumps are rare and happen only when you hit a certain region of the state space. And so, okay, I don't know if there is a theory of this kind of processes. Now, the fact that the rate functional vanishes, where is it? Here on a large, still large portion of the state space is not very satisfactory. So it means that here you could have 0 for some a, and this would tell you nothing. Okay, here we would have less than 1, so this would not be interesting. So you have to go to a further order in this kind of expansion, and it turns out that now we can find the. So there is just one order which is polynomial, one additional order which is polynomial. So at speed log t, we do not really have the exact value of the rate functional, but we can bound this from above, from below, and this is 0. And so, and again, by contraction, we can obtain. So we can study also what happens in this flat region, essentially. Okay, so we can go to a finer scale and see the behavior of the. Okay, so from the point of view of the, so this concludes the second part on large deviations. The third part on the scaling limits is still in project. So actually, we are even discussing whether this has a meaning or not for the hydrodynamic limit. So sorry, if this has a meaning or not, because the temperatures are fixed. So in some sense, this is not. So perhaps the hydrodynamic limit is not really very interesting, but at least the fluctuation should be interesting and should give rise to a stochastic PDE. We have not done this yet. I hoped I would have some results for today, but the point is that the finite dimensional system still has rather mysterious and intriguing aspects that we want to explore. So perhaps at the next SPDE meeting, if I shall be invited again, which is not sure after this talk, I will have some result, and I thank you very much for your attention.
Yeah, so other questions, comments? Oh, Professor Pierre. No. I mean, I had a question about this domain which you described. I don't remember detail, but somehow some population dynamics models with McKendrick, I think something like that comes to my mind. They have generated with somehow similar boundary condition. Are you aware of something like that?
No, so I'd be interesting.
Maybe coincidence, maybe very different, but maybe there's something, I don't know. Certainly the generator is also the first order operator, and the domain is characterized by some strange boundary conditions. Yeah, there is some question.
Actually, I have a question about the profile when you had the 3 halves. I mean, so it was not linear, but it was linear in t to the 3 halves, right? I mean, so is it because it's not transport of energy, it's transport of something else? I mean, or do you understand what I'm saying? I mean, like if you take a transport equation and it's actually has you look at a different flux, so you rescale space appropriately, then it actually changes into something like Burger's and you get a linear profile. Do you understand like what gives rise to the 3 halves? Is there some other sort of quantity? So
I have a partial answer, perhaps to a different question. So that actually you can, if you fix any profile, you can cook up a probability. So a Markov chain here on the tanks being reflected. So which gives this profile in the limit. So in some sense, any profile can be obtained. Okay, and then perhaps each profile will have some property.
Maybe it can be understood as some kind of stretching and rescaling of space somehow, or no?
It's an interesting question. I don't know.
Yeah. So some more questions. If not, let us thank all the speakers in this morning session.